I want to present a couple of examples to you that demonstrate how we can use information about geometric series to determine convergence of certain series that we might be presented with. Here's a series that I think is geometric, and it's because I see the ends and the exponents, but it doesn't really look like the series in my theorem here, which is a times r to the n minus 1, and also n has to start with 1. Here the n starts with 0. So I still think it looks geometric, but it's not really in the right form for me to determine whether it's convergent or not, or even find the limit. So what I need to do is some algebra to the expression for this series so that it looks right, so that I can apply the theorem successfully. The first thing I'm going to do is reindex. I've done this quick and dirty, which means that originally I had n equals 0, and I know according to the theorem I'm supposed to have n equals 1, so I changed it. Notice here that this says e to the n, and when n equals 0, that means you're supposed to have e to the 1. And since n starts with 1 higher, I decided to make it e to the n minus 1. The series still starts with a term that has e to the 0 in the numerator, so that makes sense to me. Similarly, down here, the series starts with 2 to the negative 2 power when n equals 0. So now that I've re-indexed, I still want the series to start with 2 to the negative 2 power, so I write n minus 3 instead. In other words, I re-indexed. I reused the letter n as my index, but that's no big deal. This series has not changed at all. My next step is to try to, I really don't like that there's two exponents. I really want there to be an a and an r and a single exponent n minus 1, so that's crystal clear what a and r are supposed to be. The change I'm going to make here is to pull off 2 copies of that 2, actually negative 2 copies. Notice how if I add these 2 exponents together, n minus 1 and negative 2, I get n minus 3. So now that I see that these two have the same exponent, I can combine them. I have e over 2 to the n minus 1 power. Over here, I have 2 to the minus 2 power, which is 1/4, but it's in the denominator, and that's why it turned into 4. Now I'm winning. I can see that a is equal to positive 4, and I can see that r is equal to e over 2. Here's the thing, e over 2, e is 2.718, blah blah blah. When you divide it by 2, it's still bigger than 1. So I can conclude that this example diverges. Here's a second problem. Another series, again starting with the wrong index, again with 2 exponents instead of 1. So I know that this guy is geometric, I'm pretty sure it is, but it's not in the right form for me to determine whether it converges or not. So I'm going to start the same way. I'm going to re-index. This time I need n to start 1 lower. And so instead of pi to the n, I have pi to the n plus 1, so that the first term still has pi squared. Instead of 4 to the n minus 1, I have 4 to the n, so that the first term has 4 to the 1 power in it. So I re-indexed, I reused the letter n, and now the series starts with n equals 1 like I want it to. Next, I really want the exponent. I want a single exponent, and I want that exponent to be n minus 1. So on the numerator, I pull off 2 factors of pi, pi squared times pi n minus 1. In the denominator, I pull off 1 factor of 4, and I get it all arranged visually, real pretty. Now I'm happy because I think I can present this in a nice way. I think I have a here, r here, n minus 1 is exactly as it should be. The series starts with n equals 1. So I know now, because pi is 3.14159 blah blah blah, that pi divided by 4 is less than 1. This series must be convergent. Additionally, because I've taken the time to write it in a perfect form, I can keep going and say exactly what that sum is. So I have a here, this is a, and I have 1 minus pi over 4. That's 1 minus r in the denominator. And then I take the time to simplify this a little bit. I have in the denominator it's going to be 4 minus pi divided by 4. So I just divide those fractions and I simplify a wee bit. My final answer is pi squared divided by 4 minus pi.